Hello class, today I'm going to make the arrangement of the elements a little bit more complicated, and we are going to learn how we can handle that version of the elements. Okay, let's see what type of arrangement we are looking to solve this for this workshop. As you can see, we have three elements here. Element number 1, number 2, number 3. But the connections between these elements are very important, and we need to pay attention to them. Element number 1 has node 1 and 2. Element number 2 is between 2 and 3, but element number 3 is between 2 and 4. We have fixed supports for node 1, 3 and 4, so displacement for those nodes are going to be 0. For the node number 2, we are going to have displacement, and the force is given, which is P. Later we are going to assume 10, for example, Newton. For Kr and K2 and K3, to make it everything simpler, let's consider their stiffness is 1 Newton per meter. Okay, so during the lecture we learned how we can construct the stiffness matrix knowing these connections for different elements. So let's go and construct the stiffness matrix. This is the stiffness matrix we have. For element number 1, we had node 1 and 2. Let's put it there. So K1, it is going to be at row 1, column 1, negative K1 here, negative K1 here, and positive K1 here. So we covered row 1 and 2, column 1 and 2, because we had nodes 1 and 2, and element is between those two nodes. For the element number 2, it is between node 2 and 3. Let's go and put it between 2 and 3. So 2, row 2, column 2, and 3, row 2, column 3. So these are going to be our cases for, let me make these close, so because this is the position. It is going to be for element number 2. Element number 3 is between node 2 and 4. So we need to pay attention between 2 and 4. So row 2, column 2, again here, like the others. We need to have K3 here. And then 4, we need to have K3 here. And then the other negatives are going to be here. So the rest is going to be 0. We also know that U1, U3, and U4, they are 0, they are boundary conditions, fixed supports, so all of them are 0 except U2, which we need to find. And we don't know what is F1, F3, F4, but we know P, which is going to be 10. So let's go and start writing our code. I'm opening a script file. Let's start with clearing everything. Now for this case, we know that connections are very important. So we need to have a matrix to show the connections. So connections add elements, and I'm going to create this element nodes matrix to save those connections. The first element is between node 1 and 2. Next row is going to be for second element between 2 and 3. The other row is going to be between 2 and 4. Done. So I saved all the connections of the elements. Let's extract number of elements. Number of elements. So the number of elements is going to be the number of connections we have. So let's extract that way. So number elements is going to be size of that matrix which we defined here. Control C, Control V. But the size of this matrix is, there are two numbers for row and columns. So the number of rows is going to be the number of elements. So I want the first number. So here I mentioned, give me just the first number. I don't want all of them. So we got the number of elements. How many nodes? Let's assign the number of nodes. Number nodes. We know that we have 4 nodes. Let's write the node for that. Number of nodes. Okay. Now we need to construct our displacement, force, and stiffness matrices. So displacement and force and stiffness matrices. So, okay, we know that displacement matrix should be a column matrix. So displacement is going to be equal all zeros for now. What is the size? Size of the nodes. We already know that number of nodes is here. So as I said, displacement is supposed to be a column matrix, so I put 1 to have 1 column, but this many nodes which we needed. For the force, similar. Forces, zeros, and let's copy the rest. Because the number of forces is supposed to be equal to the number of displacements for which assigns for each node. And the stiffness matrix, again zeros, and it's n by n, the number of nodes we have. So let's write number nodes. Done. So this is going to be, for example, number of nodes is 4. Here the stiffness matrix is going to be 4 by 4 zero matrix. The next step is going to be assigning the force we had. So applied force is going to be 10. We decided this P to be 10 Newton, for example. So I need to assign that value here inside this force matrix. So let's see that P is applied to node 2. So node 2 is supposed to have this force. So force at second row must be equal 10. Done. Now let's construct the stiffness matrix. So stiffness matrix. So I'm going to write a for loop. From 1 to the number of elements. Okay. So we need to take care of the connections, because as you remember, depends on the connections we have, we assigned the K1, K2, K3 to their positions. Remember, the number 3 was between 2 and 4, so we put here at 2, 2, row 2, column 2, and use row 4 and column 4, and nothing for 3 because element 3 was between 2 and 4. So the connections are going to be very important. That is why I'm going to consider those connections. Let's define element degree of freedom. Element degree of freedom. This is going to save the connections of each element for me to show. So element nodes, remember here, element nodes, it saved, each row saved the connections. So I'm going to extract. Let's extract the, for example, first row. So this is going to extract. So basically with this line I'm saying put the first row, because E is going to be 1 at first, put the first row of this element nodes, which is the connections. Here it's a 1 and 2 for element number 1 inside this element degree of freedom parameter which I defined. Then do the stiffness arrangement. So stiffness matrix supposed to be equal. Let me, where to put at those connections. So put those connections point. I don't want to put anywhere else. Again, similar to the last session, you must repeat this because you want to assign all the values you're putting or adding to the stiffness matrix to save in the stiffness matrix itself. And this is going to be 1, -1, the next row, -1 and 1. Done. So here I'm going to identify the connections and then tell stiffness matrix use those connections to modify the stiffness, the global stiffness matrix. I don't want to modify anything else. So for example, for element number 3, when E reaches to 3, here I'm going to transfer or copy the element connections for row 3. Here row 3 is between 2 and 4, so inside element degree of freedom, and then stiffness of the 2 and 3 of the rows, 2 and 3 of the columns, are going to be, we are going to add these 1, -1, -1, and 1 to those positions of the stiffness matrix. So we're not going to make mistake anywhere. And we decided to consider K1, so we don't, and all of the K's are similar, so I didn't consider any different stiffness matrix. But adding different K's would be very easy. Okay, done with the constructing stiffness matrix. Now we need to apply the boundary conditions. Okay, let's go back to the picture. The boundary conditions are here. Node 1, 3, and 4 are going to be fixed support, and the active node, which is going to have a displacement, is going to be node 2. So prescribed degree of freedom, this is just name, is going to be 1, 3, and node 4. These nodes are the boundary conditions prescribed, and we know the displacement, they are going to be 0. Let's assign the free degree of the free or active node. So active node, degree of freedom. Here I'm going to use set difference. Set difference, which is going to find the difference between the first matrix and second matrix, A and B, which I'm going to put here. So the first matrix is going to be all of my nodes I have, 1 to 4. The second matrix is going to be boundary conditions prescribed. Here it's 1, 3, and 4. So the difference between is going to be node 2. Automatically, basically, I'm extracting which node is going to be active, because later when I'm doing calculation, I don't need to do calculation for the boundaries. They're already given. So let's write 1 to 4, 1 to number of nodes, and transpose it to make it vertical or column matrix, and compare that matrix with this matrix. Let me copy it, otherwise I'll make a mistake. Close the parentheses. Now it is going to give me the active node, which is going to be the difference between fixed node and the total nodes. Okay, we are ready. Solution. Let's solve it. So displacement, where is it? Displacement is going to be equal stiffness matrix, where are you? Here, of active node. I don't want to solve the other boundary conditions, boundary nodes. And where is force? Again at active node. So now I can get the displacement at exactly that active node. I can do a bit more, make it much more beautiful. Let's write another parameter, displacement. For example, number 1 is going to be zeros, and number nodes, it is going to be column. So I created an empty matrix. Now I'm going to put all the calculated displacement inside this matrix. So let's Control C. So displacement of active node supposed to be equal whatever we calculated here. Why I didn't put the values of the other displacement? Because I already know that we had fixed support, and for number 1, 3, and 4, displacement supposed to be 0. And I created this displacement 1 with zeros. So by changing just the active node, the rest is going to be okay. Excellent. Now let's run it. I didn't save it. Let's save. This time I'm going to call it number 2. Save it. Okay, it says we can't save it like this, so save. Okay, now it is saved and we can run it. Let's see what is the value. So displacement at second node is going to be 3.333. Do you want, what else we want to look for? Let's look for forces. 0, 10, the other 0, which is excellent, and we were looking for those displacement. Okay, thank you very much. And if you want to see more details, you can easily stop it wherever you want. For example, here, let's stop it, run it, and you can see, okay, what type of matrices we have. This is the matrix for connections. This is the number of the elements which we extracted from the connection matrix. Displacement, just column matrix. Force, again column. Stiffness matrix, currently it's empty. This is the, if I step forward, I expect to have 10 at the second row, which is there. And then we can see what happened here. This is first connection. So I saved first connection 1 and 2 inside the element DOF, and then stiffness matrix is going to be 1, negative 1, negative 1, 1, just for first and second row and columns. So if I do once more, now the connection saved is the second one, 2 and 3, 2 and 3, and stiffness matrix is there, just applied for 2 and 3. And finally, for the last one, 2 and 4, which is the third one, and stiffness matrix is like this, between 2 and 4. And the rest, if you were interested, just check it. Okay, thank you very much. See you next time.